Algebra 2, Chapter 12, Section 3, Solving Polynomial Equations. Solving p of x equals 0 for some polynomial p of x is equivalent to finding the zeros of the polynomial. In other words, finding where the value of the polynomial is 0 will help us solve the equation when it doesn't equal 0. That may seem obvious, but that's important. The polynomial has a factor inside of it. So if we think of the polynomial, it has a factor inside of it of, a bunch of stuff times x minus k and a bunch of other stuff all multiplied together if and only if the polynomial's output when we put in k is 0. So if we find zeros, then we find factors. And if we know factors, then we know zeros of the polynomial. This is very important and allows us to be able to use factoring to solve polynomial equations and use graphs of polynomial equations or other ways of finding zeros to find factors of polynomial equations. Because the most factors a polynomial can have is its degree, the most zeros a polynomial can have is its degree. An even degree polynomial can have no zeros, while an odd degree must have at least one zero. This is another important fact about how many zeros you can have. So first of all, remember zeros are factors, and factors are zeros. The most you can have is the degree of the polynomial, but the least, so if you have an even degree, say your polynomial was a degree 2, you could have no solutions and no zeros of the polynomial. This can happen, for instance, if your polynomial is x squared plus 1. This will never be equal to 0. So there will never be a 0. There will never be a solution when p of x equals 0. There will never be any factors. So you cannot factor this. But with an odd degree, you must have at least one 0. And by extension, you can always factor an odd degree polynomial at least once. Now, that factor may not have integers. You may not have an integer factor, but you can always find at least one 0 for a degree 3. So if you had x cubed plus 1, it'll always be 0 somewhere because the graph of x cubed is such that somewhere you're going to cross the x-axis. Let's use these ideas to help us solve some polynomial equations. We'll start by solving this equation, x squared equals x cubed. And you've seen me solve similar things by saying x is not 0, x is 0, but let's think about this as a polynomial equation. If we think of it as a polynomial equation, we need to make it equal 0, so put everything on one side. We want to know when is x cubed minus x squared 0. And now if we factor, we can find the solutions. So if we take out an x squared, we're left with x minus 1 as our factorization of the polynomial. Now we could use the zero factor principle. So remember the zero factor principle from before. We talked about this earlier in the year. The zero factor principle states that for a times b to equal 0, either a is 0 or b is 0 or both. So one of them has to be 0. So in order for this to be 0, either x squared is 0 or x minus 1 is 0. Remember, the zeros are the factors. And there are solutions. X is 0 or x is 1 are the solutions to this equation. Now let's solve a more complicated polynomial equation. At first hand, this looks like a cubic equation we're not going to be able to solve. But let's distribute and see if what we end up with is not cubic or if we can factor it somehow. So w cubed, so we have to basically distribute this over itself 3 times. W plus 1 cubed means multiply it by itself 3 times. So you'll have w times itself. Maybe let's not skip any steps. We'll just do the quadratic here at the beginning. W squared. W plus w is 2w, and then 1 times w plus 1. And if I went over that too fast, just review that on your own. Make sure that makes sense to you. And then distributing the w plus 1, we get w cubed plus 2w squared plus w. That's the w times this quadratic, and then times 1 will just be the same thing, w squared 2w plus 1, which is w cubed plus 3w squared plus 3w plus 1 equals the left-hand side, w cubed minus 2w minus 1. Now, put everything on one side. Let's put it on the right. We have w cubed minus w cubed. That's going to be 0. Now we're adding. There's nothing, no quadratic on the right, left, no quadratic term. So 3w squared stands. Adding 2w, we get 5w. Adding 2 to 3. Adding 1 to 1, we get plus 2. Now we have a quadratic. We could solve this by factoring. We could solve this with the quadratic formula. Let's see if we can factor this first. It's a little trickier because we have the 3 here in front of the w squared. So we would have to find numbers that multiply to 6 and add to 5, which would be 2 and 3. So we could try that and see if we can make that work. So if it was 2 and 3, we would have well, we have to think about this for a second. Hold on. So to factor, we had to go back and review factoring a little bit. So remember, the 2 and the 3 tell us how to break up this middle part to factor by grouping. So we can write it in either order. And let's erase the parentheses. That's not right yet. So break up the middle term, 5w into plus 3w plus 2w, and then factor the first pair of things, the second pair of things. The first has a 3w. That leaves us with w plus 1. The second has a 2 in common, which also leaves us with a w plus 1. Factoring the w plus 1, which is common out, we get 3w plus 2 times w plus 1. And now we can find our zeros from our factors. So using the zero factor principle, we write 3w plus 2 is 0 or w plus 1 is 0. So w would be either negative 2/3 or it would be negative 1. Let's solve 2x cubed plus x squared minus 12x plus 9 by graphing the polynomial. Okay, and then we're going to factor using our solution. So how do we graph this? Unfortunately, it's going to be a little tedious. We need to first get some axes. So here's x, and let's make a y-axis. Often you'll be given the graph, but this time let's actually try to do this by graphing it ourselves. Okay, so here's our x, and here is our polynomial of x. We're going to graph our polynomial. We can start by graphing the constant term is the y-axis, the y-intercept. So let's put that right here. So we'll have 9 at 0 when x is 0. Now we just need to plug in some numbers and get some outputs. So let's plug in 1. You can use a calculator to do this faster. So if we take 2 times 1 cubed is just 1. So we can just really just write 2 plus 1 squared is 1. 12 times 1 is minus 12. Sorry, minus 12 times 1 is minus 12 plus 9. That gives us 0. So as we were graphing here, we already found one of our zeros. At 1, we'll have a 0. Okay, let's try 2. So at 2, we're going to get 2 times 2 cubed plus 2 squared minus 12 times 2 plus 9 gives us 5. So when we have 2 as an input, we get 5 as an output. How about 3? 3 might be really big. Let's try it. Let's see. 3 cubed plus 3 squared minus 12 times 3 plus 9, 36. So at 3, our output is 36 for our polynomial function. 18, 27, 36 would be way up here above the word polynomial. So it kind of ran out of space on our graph here. Let's kind of visually show these axes go at forever. They don't really stop. It's just a way for us to represent our orthogonal axis system. Now let's try negative. So 2 times negative 1 cubed would be negative 2. But negative 1 squared is 1. Minus 12 times negative 1 would be 12, plus 9 gives us 20 at negative 1. So 9, say 20 is here, and negative 1 would be around here. So you can see we're kind of going down here. Something happens here, we can switch directions somewhere, come back way up this way. Let's go ahead and do negative 2. We'll put in negative 2 and negative 3, and we'll even try negative 4. Let's see what happens here. Negative 2, we get 2 times negative 2 cubed should be negative 8, plus negative 2 squared is 4. Negative 12 times negative 2 would be plus 24 plus 9, gives us 21 at negative 2. 21 at negative 2. Negative 3, 2 times negative 3 cubed, that'll be negative 27, plus negative 3 squared is 9, minus 12 times negative 3 will be plus 12 times 3. Oh, that gives us 0. So we found another 0 as we were graphing. And let's see what happens when we put in negative 4. Negative 4 cubed is pretty big, but I mean negative, so really small really. Plus negative 4 squared will be positive 16 minus 12 times negative 4 plus 9. Negative 55, which is way, 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 way down here. So we'll just go ahead and draw a tail that shows that the graph goes really fast down because we don't even know where negative 55 would be on our graph here. So next we need to think about this polynomial a little bit. It's x cubed, which means it's cubic. The degree is 3, which means we could have at most 3 solutions. We clearly have a 0 at negative 3 and a 0 at 1 from as we graphed. What's not clear is if the graph bounces here and goes up, or if it crosses somewhere in this region. So we need to graph this region more clearly. From what we've already seen, what we've already plugged in, we're going to definitely have this shape here, and this shape here. But this region between 0 and 2 needs to be defined better. So let's grab our calculator again. Put in 0.5. 2 times 0.5 cubed plus 0.5 squared minus 12 times 0.5 plus 9. 3.5 for 0.5. 3.5 at 0.5 would be around here. Let's put in 1.5. 2 times 1.5 cubed plus 1.5 squared minus 12 times 1.5 plus 9, 0. So we found another 0 at 1.5. So presumably the graph dips right below the axis here. Let's prove that by putting in a number in between, which would be 1.25. 2 times 1.25 cubed plus 1.25 squared minus 12 times 1.25 plus 9. Negative 0.53125, around negative 0.5. So we can negative 0.5 is just ever so slightly below the axis here. So we can fill in the graph now with our sort of interpolation of these points. Carefully connect the dots, basically. And we have a graph. And by graphing, I've already seen that x is 0. Sorry, p of x is 0. So zeros are at x is -3, x is 1, and x is 1.5, which would be our solutions to our equation equals 0. Now that we have our solutions, let's now factor our polynomial. So we know we can write now the polynomial out in factored form kind of like this. There's some number here, k, we're not sure of just yet. We'll find it in a second. So we're not trying to factor this whole thing. We're using the zeros to write the factorization. So we don't know what k is just yet. So remember, each factor, because of the zero factor principle, each of these has to equal 0. This will subtract this number. So you'll have this whole problem of a form with a negative in it again. So it's x plus 3 to get a solution of x minus 3. X is minus 3. X minus 1 to get a solution of x plus 1. And x minus 1.5 to get a solution of 1.5. So what would this k be? Well, that can be found by thinking about the leading term. So the leading term would be 2x cubed right here. So in order to get 2x cubed, k is going to have to be 2. Okay, so we can now think about this a little bit more. Say, okay, well, we have this 2 in front, but we have this 1/2 in one of our factors. We can make this even simpler by multiplying the 2 into this factor here. So we'd have x plus 3, x minus 1, 2x minus, and this is 3/2. So we multiply by 2, we get minus 3. And now we have this nice, pretty factored form of this cubic. And all we did to find that was find zeros. We found zeros by graphing. And as we graphed, we saw some zeros. We had to kind of think about the shape in order to get other zeros. Then from the zeros, we could factor the polynomial. Let's show that 2 and 3 are the only consecutive positive integers such that the cube of the first is 1 less than the square of the second. That sounds like a lot to think about. Okay, so we have consecutive positive integers. Let's say that the first of them is n, and the second would be then n plus 1, because they're consecutive. So this could be 3 and 4, 5 and 7, 6, n could be 10, and then n plus 1 would be 11. So we're wanting to show 2 and 3 are the only consecutive positive integers such that the cube of the first, so here's the first, the cube of the first is 1 less than the square of the second. So the cube of the first minus 1 should be the square of the second. Those should be equal. So we can write an equation here. Hold on, let's think about this. The cube of the first, so I wrote the minus 1 in the wrong place. The cube of the first is 1 less than the square of the second. So 1 less than the square of the second means we have to take 1 away from the square of the second. That should be the cube of the first. So basically we're wanting to show that the only solution to this, we want to show the only solution to this is n equals 2 for positive integers. Okay, so we might get some negative or 0 answers. So to show this, let's solve the polynomial equation we would get. N plus 1 squared gives us n squared plus 2 plus 1, 2n plus 1 minus 1. So we're moving n cubed to the left, to the right. Moving it from the left to the right, we get minus n cubed plus n squared plus 2n plus 1 minus 1 is 0. Okay, now let's factor the n out. we get minus n squared plus n plus 2 times n. And now we can factor this quadratic. We need to find, well, we can think about pulling a negative out here to help us factor the quadratic so we don't have to worry about the coefficient of n squared not being 1. So without n squared being 1, all we need to do is find numbers that multiply to minus 2 and add to minus 1, which would be 2 and 1, of course. So we have to do n minus 2, n plus 1 to get that to work right. So we have minus n times n minus 2, n plus 1. That works because you have n squared. Minus 2, n plus 1, n is minus n, and then minus 2. So we can write three equations from the zero factor principle. Minus n is 0, n minus 2 is 0, n plus 1 is 0. Minus n is 0, so that would be n is 0, because 0 times negative 1 is still 0. N is 2, or n is minus 1. So there's three answers to the equation, but only one of them is positive, where 0 is not positive. So we've shown that the only positive integer solution is 2. So there are no other positive integers where this equation is true. Now, let's find a polynomial from some zeros. So find a polynomial that's degree 4 and has the following zeros. Okay, since it's degree 4 and there's 4 zeros, we don't have to add any extra things to make the polynomial degree 4. And I'll explain that in a minute. So we could just write t, remember we have to negate each of these, t plus 1, t minus 0, which is t minus 1, t minus 2, and that's it. We're done. That seems really simple. That's all we have to do. We could multiply this out to show that it's degree 4, but that's obvious. But the leading term is going to be t to the 4th. What if it said, find a polynomial that is degree 5 and has these zeros? What we could do is square any one of these. And what that will do is put 2 zeros at one spot. And we'll talk about that in a minute, what the graph will look like when there's more than 1 0 at the same spot. We could apply this if it said degree 9. We could just put, there's 4 here. We would need to put the 5th power to get t to the 5th. And that would give us t to the 8th, and we could put a squared here. That would give us a possible one that has just these zeros, so no other zeros. Okay. So now let's think about this. Without solving, how many solutions could each equation have? Well, this a is degree 4, so it could have at most 4. And we know since degree 4 is even, it could have the least it could have is 0. B, this one, let's see, the degree of this isn't obvious because we have to do some work to find a degree. 3x cubed minus 3x is 1 plus 3x cubed. When we subtract the 3x cubes, the cubes go away. We have 0 is 3x plus 1, putting it all on one side, so we have a polynomial equation. Remember, the polynomial equation is polynomial of x equals 0. And here we have a degree 1, so there'll be one solution. And we know that's exactly right because 1 is odd. So it has to have at most one solution and at least one solution. So there's exactly one solution. C, we have degree 3, but doing some simple quick analysis, we see this factor, if we were to write an equation, we would get no answer, because, at least not a real numbered answer, because we would have s squared as negative 5. So there's only going to be one real, which is what it's really asking, how many real numbered solutions can each equation have? We're not talking about complex numbers with polynomials. Not in this class. We're only talking about complex numbers with quadratics specifically. So, in general, with polynomials, we're not. So this would be 1. And again, the degree is odd, so there has to be at least 1. So we have one solution. So we can't just blindly find the degree. When we have more information obvious by looking at the form of the equation, we should integrate that information into our answer. So we know that there can't be more than 3, but this eliminated 2 of the possible zeros, because this can't be 0, s squared plus 5, at least not with real numbers. So this brings up again, what does the graph look like when we have multiple zeros? And this would be a good time to go back and review power functions. So go back and review power functions if you need to, and look at the slides and videos about the shape of the various power functions. And really all you need to worry about is the power functions that are positive integers that would fit into polynomials. So x squared, x cubed, x to the fourth. And real quick, the shape of x is a line, x squared we have a parabola, x cubed we have this little thing that bends, x to the fourth we end up with a shape that's like a parabola but much more squared off, maybe not quite that much, something like this, and so on. Remember, each time the powers go up, the shape gets steeper. So you get more jagged edges. They never get completely jagged. They just get steeper. So if we have a graph with just plain old zeros, say we have a graph with a 0 at -2, 0 at 0, and a 0 at 3. The graph might look something like this. It'll cross, and it'll cross. That's supposed to be at 3. The graph will touch the axes at the zeros, and it'll just go straight through it. It won't bend or twist as it's going through the graph. These are all simple zeros, or single zeros. Simple zeros. So what happens when you have a double zero? If the 0 happens twice. So suppose you have a single or simple 0 at -3, but at 2 you have a double 0. Well, at -3 the graph will go straight through the axis. But at the double 0 you'll have a shape that looks like a parabola. The graph will come down, it'll touch the axis and bounce back up. And so in this little local region of the graph will look just like a parabola touching the axis, which will look a lot like the graph of x squared. Just the plain old graph of x squared. I don't know why I was showing you graphs of x squared shifted here. Let's just think about the power functions weren't shifted or scaled. They all go through the origin, right? What about a triple zero? If you have a triple zero at a particular point, let's say, same graph, simple 0 at -3, but triple at 2. So you basically would have a polynomial that's x plus 3, x minus 2 cubed. So here you would have x plus 3, x minus 2 squared. And this one has the 0 at 2, -2, and at 3. So you would have a polynomial like this. So these are just possible polynomials, depending on, sorry, this one had 3 zeros. Let's fix that. These are just possible polynomials. The particular y-intercept would tell you the exact polynomial by finding some constant here we'd have to multiply by. So here we'd have some constant times x plus 2 for the 0 at -2, x for the 0 at 0, and x minus 3 for the 0 at 3. So that would be a possible formula for these simple zeros. For the double ones, we would have a squared on the double 0. And the triple one, we have a cubed at the triple 0. So we would, again, simply go through at minus 3, and then the graph will be shaped like cubed at 2. So it'll come real close, touch exactly at 2, and then go down. So you have this cubed shape. Now this one's inverted, but it's the same shape locally near the 0. It's triple. So you can identify simple, double, and triple zeros by looking at the shape of the graph near the 0. If it just goes straight through, it looks a lot like a line when you zoom straight in. That's because it's a simple 0, or single 0. When it's double, it'll look a lot like a parabola. It'll kiss the graph and bounce off. If it's triple, it'll look a lot like cubed. It'll come down to the graph, kind of like a gentle slope, and then come back down again. Make this kind of this kind of hump look, where it comes up, slows down, and then starts back going fast again. Kind of like that. And again, it can be either direction. And if you had a quadruple 0, it would be shaped, suppose this was quadruple, it would be shaped steeper, more like x to the 4th, like this, at 2. So you can kind of identify by the steepness which power it is. That's a little trickier. It's easy to distinguish single, double, and triple from each other. So they're all very different. Single goes straight through, double bounces, and triple goes up, slows down, and goes up again, or down, slows down, and goes down again, depending on the sign.